Hello friends, today I will discuss about different protection used for transformer. The difference relay used for transformer has been shown in this diagram. In the transformer there exists HB side winding and LB side winding. In the HB side there exist CTs. From the CT secondaries the relays are connected for both HB and LB side. The main relay is here 87T or differential relay, and also 64 HB and 64 LB, which is called the HB REF relay and LB REF relay. Now HB REF and LB REF relay can be connected from bushing CT if bushing CT is available in the transformer, and in the HB side and LB side relay is connected, that is 51 HB and 51 LB, which is called HB backup over current relay and LB backup over current relay. And there exists also the transformer trouble relay, which is actuate due to internal fault of the transformer, which is the gas actuated relay, that is called Buchholz relay, and also PRD. PRD means pressure relief device. And there exists also the temperature related relay, or OTI and WTI. OTI is oil temperature indication. If oil in the transformer increase to certain level, then this relay will operate. And also WTI, which is called winding temperature indicator. Now I will discuss in details one by one in this video. Before going through this video, you can do subscribe my channel and also press bell button for notification of videos to be uploaded in future. Now first topic is restricted earth fault relay. Restricted means it is operate if earth fault occur to a particular zone. Now the 10 MVA 33 by 11 kV DYN11 type transformer diagram has been shown in this diagram, where the REF relay connection has been shown for HB and also for LB side winding. Here the P1 for phase cities should be connected in the bus side, and P2 in the phase cities shall be connected in the transformer side for both HB and LB side. And for delta side, all the in the secondary side of the CT, all the S1 terminals sorted and all the S2 terminals sorted and connected to the HB side REF relay terminal. So if any fault occur in the inside zone, that is towards the transformer side, then only this relay will operate. Again for LB side, and the connection has been shown. Connection is that is all the phase cities should be connected in the bus side. P1 shall be connected to the bus side, that is towards 11 kV side, and for NCT neutral city, P1 shall be connected in the earth side. Connection is similar for HV side REF, that is all the S1 terminal including NCT's secondary S1 should be connected together and connected to the one end of the 64 LB, that is restricted earth fault relay, and all the S2 terminal including NCT's secondaries should be connected together and connected in the other end of the relay. If any fault occur in the inside zone, then only relay operate. Now the question is, if the differential relay is used, now why should we use the REF relay? Now differential relay will be unable to detect fault if earth fault occur very close to the neutral. If earth fault occur very close to the neutral, then the phase city will sense a minimum amount of current, and thereby most of the current will be fed from the neutral city, and that is why REF relay is introduced to detect this kind of fault. So friends, I have a lot of videos on REF relay. You can go through the video for details, and that is why the resistance is used, and also use of METROSIL in the REF relay. The link is given in the in this video. You can go through the video, you will get details knowledge of the RF relay. Now the differential relay. The differential relay connection has been shown in this figure. Here both the HV and LV side cities are required for differential relay. Again for phase and the magnitude matching, the ICTs are used both in the HV side and LV side as shown in this diagram. Here the connection diagram is delta Y, and since it is DYN11, that is why there will be plus 30 degree phase shift from HV to LV side, and that is why in the star side we use ICT as star delta. Star delta is used, the reason is to eliminate the zero sequence current in the star side, and also delta is used to match the phase shift occurred in the primary side. Again in the HV side, since it is a delta connected, the ICT is used is star star. Only here magnitude matching is done, so that under full load condition that 1 per unit current will flow in the relay. Now if I1 is the HV side current flow, that is in power unit quantity, and I2 is the current flow in the differential relay due to current flow in the primary side of the LV side, then the restraining force is given by I1 into N by 2 plus I2 into N by 2. Here the restraining winding has N by 2 winding each. So the restraining force is proportional to N into I1 plus I2 by 2, and differential force is given by the vector sum of I1 plus I2 into N, and number of turn in the operating coil is N. Now when the differential force will be greater than the restraining force, then only relay will operate. And this is the characteristics of the differential relay, and that is mainly static relay. In case of numerical relay, there is no external ICTs is required. If we put the vector group of the vector group of the transformer and the phase CT ratio of the HV side and LV side, and also the transformer capacity, then it will automatically calculate which ICTs or virtual ICTs is required. It will automatically calculate, and phase matching and magnitude matching is done automatically in case of numerical relay. Now what should be the ratio of the ICTs has been shown in this diagram. It will depend on the capacity of the transformer and also the ratio of the HV side and LV side CT. Here the capacity is 10 MVA 33 by 11 kV, that is HV side is 33 kV and LV side is 11 kV, and HV side CT ratio is 400 by 1 and LV side CT ratio is 600 by 1. Again since the HV side full load current is 175 ampere and LV side full load current is 525 ampere, due to flow in the primary side full load current that is 175 ampere, the ICT's ratio should be such that in the differential relay 1 ampere current flow in the operating or in the restraining coil. Again for LV side, for the flow in the HV side, LV side primary current 525 ampere, the restraining current should be 1 ampere in magnitude. Since it is since ICTs are used in the HV side is star star, and the secondary current is in the 400 by 1 CTs is 0.4375 ampere, the ICTs in the star-star connection should be 0.4375:1. That is, if 0.4375 ampere flows in the primary of the ICTs in the star-star, then in the secondary of the ICT or in the differential relay restraining current 1 ampere current magnitude will flow. Again, since it is a delta y and the vector group is dy11, there is a phase shift of plus 30 degree in the LV side to match this phase shift, and also to eliminate the zero sequence current we use the star delta. Here the vector group for ICTs for star delta should be YD1 type to match the phase shift occurred in the HB side. That is, here plus 30 degree phase shift occurred. That is why in the YD1 their phase shift is minus 30 degree. And the magnitude and the ratio should be such that if 525 ampere current flows in the primary side, and then in the operating in the restraining coil 1 ampere magnitude current will flow. Since CT ratio is 600/1, the magnitude of the secondary current is 0.875 ampere, and that is why the ICT ratio is 0.875:1 that is 0.577 current will flow in the winding, and as a resultant current it is 1 ampere current flow in the restraining coil. Now the characteristics, dual slope characteristics is used in place of differential relay. The initial setting is given so that due to mismatch of the tap the relay shall not operate on, and slope is given so that under through fault current the relay shall remain in stable condition. The characteristics has been shown. Here the x-axis shows the restraining current in per unit quantity, and y-axis shows the differential current in per unit quantity. You can go through the description, the link in the description box regarding the differential relay. The link is given in the description box. Please go through the video. You will get detailed knowledge about the characteristics of the differential relay. Now, how does the ICT match the current, and under normal condition how does the differential current is 0 and the operating current is this differential current is 0 and the restraining current is 1 plus 1, that is under full load condition it is 2 per unit has been shown in this diagram. Now since under full load condition, assume that the transformer is running under full load condition, that is 175 ampere current flows, and that is why in the secondary side in the ICT's primary the current magnitude and angle has been shown. That is, for red phase it is 0.4375 at an angle of 0 degree, and for yellow phase it is 0.4375 at an angle 120 degree, and for blue phase it is 0.4375 at an angle 120 degree. Since ICT ratio is 0.4375:1, in the secondary side or in the differential relay side, the current magnitude of the current with the angle is for red, yellow and blue phase is 1 at an angle 0 degree, 1 at an angle minus 120 degree, and 1 at an angle 120 degree. Again for the LV side, as the full load current is 525 ampere, the secondary current shall be 0.875 at an angle of minus 150 degree for red phase. Now the question is why the current is 0.875 at an angle of minus 150 degree. Now since it is a dy11 type, there will be a phase shift of plus 30 degree. That is the magnitude of the angle in the HV side for red phase will be 525 at an angle of 30 degree. Now the current flows in the HV side cities from P2 to P1 direction, and that is why there will be phase shift of 180 degree in the secondary side, and therefore the angle is and that is why the angle is minus 150 degree for red phase. Similarly, for yellow phase it is 0.875 at an angle 90 degree, and for blue phase it is 0.875 at an angle of minus 30 degree. Now ICT ratio is 0.875 is to 0.577. In the phase current in the delta side shall be 0.5777 at an angle minus 150 degree. For red, for yellow it is 90 degree, and for blue it is minus 30 degree. So the line current for the delta side or the current flows in the differential relay should be vector sum of the red phase and the blue same red phase current minus blue phase current. Red phase current minus blue phase current, which comes as 1 at an angle of 180 degree. Similarly, for the line current for yellow phase in the ICT secondaries or in the differential relay restraining coil, it will be yellow phase current minus red phase current, which comes as 1 at an angle of 60 degree. Similarly, for blue phase it is blue phase current minus blue phase current minus yellow phase current, which comes as 1 at an angle of minus 60 degree. Now for red phase, the differential current is the vector sum of the 1 at an angle of 0 degree and 1 at an angle of 180 degree, which comes as 0. Similarly, for yellow phase, the differential current is 1 at an angle of minus 120 plus 1 at an angle of 60 degree, again which comes as 0. Again for blue phase, the vector sum of 1 at an angle of 120 plus 1 at an angle of minus 60 comes as 0. That is why the differential relay remain in stable condition by this arrangement. Now the backup overcurrent protection for the transformer. Backup means if any external fault occur in the transformer, that is fault occurred in the outside zone of the differential zone, then only as a backup protection it shall operate. It is nothing but overload protection of the transformer. Setting is normally set as 110 to 115% of the full load current for HV overcurrent and LV overcurrent relay. Now consider a feeder A is connected in the 11 kV side from the transformer 33 by 11 kV in DY type as shown in this diagram. Again in the 11 kV side a feeder is connected and from the CT secondary of the feeder relay is connected is 50N and 51, that is back overcurrent relay and earth fault relay. Now under normal condition, if any earth fault occur in the feeder, then 50N of the feeder relay shall operate. If any overcurrent fault occur in the feeder A, then 51 of the feeder relay shall operate to clear the fault. Now under any abnormal condition, the 50N or 51 of the feeder relay fail to clear the fault due to problem of the relay or due to problem of the circuit breaker associated with the feeder A, then only as a backup of earth fault 50N of the LV side or star side side of the transformer shall operate as a backup earth fault protection, and as a backup overcurrent protection, that is 51 LV shall operate. Again the 51 LV failed to clear the fault due to some reason, then only as a backup protection of the LV side, then 51 HV shall operate to clear the fault. You can go through the video as mentioned in the description box for details about backup overcurrent protection of the transformer. The construction of the Buchholz relay has been shown in this diagram. This is the transformer main tank, this is the conservator tank. It is located in the top of the transformer, and between this two tank a connecting pipe is connected. So the oil is circulated from main tank to conservator tank and conservator tank to main tank. When the oil in the transformer main tank heated, it will expand in volume. Therefore oils will some of the oil flow towards the conservator tank. When the transformer main tank cool down, the oil will the volume of the oil reduced, and therefore some of the oil from the conservator tank flows towards the main tank. This is how the oil circulation is done from main tank to the transformer conservator tank. And in this pipe a Buchholz relay is connected, and this Buchholz relay will operate when any internal fault occur in the transformer winding or incipient fault, that is fault is very low, and it will detect early fault whether the other relay that is REF or differential relay will not be able to detect this kind of fault due to low amount of the current. Now this is the construction of the Buchholz relay. In this Buchholz relay it is dome shaped, and in this Buchholz relay this pipe is connected. This is the inlet valve, and this is the outlet valve. This outlet valve is connected to the towards the conservator tank, and this inlet valve is connected from the main tank. So there exist two valve. In the lower portion there is the oil drain valve, and in the upper portion it is a gas release valve. When gas accumulated in the upper portion of the Buchholz relay, it is collected and it is tested whether it is inflammable or not, and by testing these gases we can assume whether any internal fault is occur in the transformer or not. In the upper portion a float is connected by means of a pipe, and this pipe is connected in a fixed point. It is called hinge. In the lower portion a flap is connected. In the flap there is two position. One position is connected towards the flow path of the oil as shown, and the other position is tilt slight angle, so that under normal condition the Mercurry switch connected in this path will not make, and this is the hinge point. So under normal condition oil is filled up to this level, and therefore this float will remain in this position, and this pipe connected with the float will be inclined from the hinge point in such a way the Mercurry switch will not make the two electrode. And from these two electrode two cables are connected from alarm circuit and also from trip circuit, and from one of the cable is connected to the auxiliary relay in the control and relay panel, and other cable DC positive is connected. If this Mercurry switch make, then this DC will come from this electrode, and since this Mercurry is make, this two electrode come to this cable, and the relay connected with this auxiliary relay will make or actuate, and therefore a trip signal will be generated and it will trip the circuit breaker. Similarly, the auxiliary relay connected from this Mercurry switch, if this Mercurry switch make, then the DC connected in this cable will through to this cable, and therefore the auxiliary relay connected with this cable will actuate, and it will send a Buchholz alarm signal for slight internal fault in the transformer. Now when any internal fault in the transformer winding or interturn short occur, and due to this fault there will be heat will produced in the winding, and therefore this heat will pass through the transformer oil in the main tank of the transformer oil. Therefore due to heating of this oil, the oil in the transformer main tank decomposed, and therefore it will generate some of the hydrocarbon gases. These hydrocarbon gases in the main tank in lighter in weight and will try to escape from main tank to the conservator tank. When these gases passes from the transformer main tank and flows towards the transformer conservator tank, some of the gases will trap in the upper portion of the Buchholz relay, and therefore since these gases are lighter in weight compared to the oil level in the upper portion of the Buchholz relay will decreased, and some of the oil flow towards the conservator tank, and these gases will fill up in the upper portion of the Buchholz relay, and therefore the float connected with this hinge and flow in the downward position and incline in horizontal position, and therefore the Mercurry switch connected with this float will incline in horizontal position. Therefore this Mercurry switch make this two electrode, and therefore the DC connected in other end of the Mercurry electrode will be flow to the another end of the electrode, and the cable connected with this electrode, and therefore the auxiliary relay connected with this cable will actuate, and it will send a alarm signal for internal fault of the transformer main tank. Now when there is a severe internal fault in the transformer, there will be more heating, and therefore the oil in the transformer main tank decomposed more quickly, and therefore more gases will generated, and also the oil in the transformer main tank expand in volume. Therefore, along with the hydrocarbon gases, the oil try to escape from the transformer main tank towards the transformer conservator tank, and therefore when the oil along with the transformer hydrocarbon gas generated due to decomposition of the oil, this will create a pressure in the lower flap. This lower flap will incline tilt in this position, therefore the other portion of this flap will move in the upward direction, and this Mercurry switch aligned in the horizontal position. Therefore the Mercurry in the Mercurry switch makes the two electrode, and therefore it will send a trip signal, and the auxiliary relay connected with this cable will actuate, and the auxiliary relay send a trip signal to the circuit breaker to isolate the faulty transformer from the system. Now PRB means pressure relief device. When the internal pressure of the main tank of the transformer reach to a excessive level, then from this device the excess pressure will be released. This is nothing but a spring loaded valve. In the valve a pin is connected with this spring, and when the due to internal pressure the spring operate in the upward direction, this pin will push towards the upward direction, and the disc connected with this pin will move in the vertically, and there are contact NO contact when the discs operate, that is discs move in the upward direction, the NO contact comes to NC position. Now when the PRD operate, that is the discs move in the upward direction, the NO contact comes to NC position, and in the NO contact in the two terminal two cables are connected. One cable is connected to positive DC, and another connected to one of the terminal of the auxiliary coil of the relay. And when this relay operate, then the auxiliary relay connected with this terminal of the NO contact will actuate, and this will send a trip signal to the circuit breaker to isolate the faulty transformer from the system. Now OTI means oil temperature indication. OTI sense oil temperature when the internal fault like insulation failure in one phase of the winding or shorted or local hotspot generate, and then oil temperature will be increased. A probe is connected or inserted in the oil of the main tank. It sends the temperature of the oil of the main tank. When the temperature of the oil reach to about 80 to 85 degree, then a alarm will generate, and when the temperature will reach about 90 degree, then a trip signal will be generated, and to trip the circuit breaker to isolate the faulty transformer from the system. Now WTI means winding temperature indicator. There exist LB WTI and HB WTI, and from the WTI for Mercurry switch is connected one is for fan control, one is for pump control, and one is for WTI alarm and WTI trip. Now it sends for WTI, again a probe is connected in the transformer. By means of it sends the temperature of the winding. It may be HB winding for HB WTI and LB winding for LB WTI. When the temperature of the winding temperature comes to about 60 to 65 degree, then fan connected in the transformer radiator will switch on, and again when the due to more load in the transformer, the temperature goes beyond 65 to 70 degree, then pumps will on there. The oil circulation will be done by means of pumps, that is it is oil natural and air force. That is cooling is done by means of firstly fans, and then cooling is done by means of air force in the radiator. And when the temperature of the winding further rises, that is 80 to 85 degree, then alarm signal will be initiated, and if the temperature rises further, that is 90 to 95 degrees centigrade, then a trip signal will be generated and the circuit breaker will be tripped.